Hi, this is the last part of the chapter 9. We're going to discuss, in this video, we're going to discuss weight and weightlessness. Let's see. Before we talk about weight and weightlessness, let's go over the gravitational acceleration that we discussed. On the surface of the Earth, gravitational acceleration is constant for every object, and that's 9.8 meter per second square. But by applying the universal gravitational law, right? Universal gravitational law, right? If you go up higher, that means that you have okay, R2D2 here. R2D2 is going to be higher than the Earth, than the surface of the Earth. Then the distance between them is going to be, when the distance between them is going to be significantly larger, if you cannot ignore the altitude, how high you are up from the surface of the Earth. It's not just the radius of the Earth, it's RE, the radius of the Earth, plus the H is large enough, then you can see that it's longer the distance, follows the inverse square law, and the gravitational force do decrease. So you would imagine that acceleration should also decrease, right? So how much actually is really less by going up farther, like away? We said it in the last lecture that universal gravitational acceleration follows the inverse square law. So if we go up the radius of the RE, Earth, one more. So if it's twice more the distance, then the force becomes 1/4. But 1/4 of the force is still significant. You still have a force that's not negligible. You still have a gravitational force. All right, so let's look at that more carefully. Let me go into share the whiteboard again. Okay, share the screen. Here. Okay. Okay, so this is chapter 9. Green again. Oops. Whoa. Okay. Chapter 9. Part 3. And today we're going to talk about weight and weightlessness. So before we talk about weight, let's go over the gravitational acceleration. So on ground, let me see, before that, I'm going to talk about Newton's universal gravitational acceleration says G m1 m2 divided by d squared. And G is equals to 6.67 times 10 to the minus 11 Newton meter square kilogram square, I believe. Right? Let me just make sure. Pretty sure that's what it is. Yeah. So this is the universal gravitational law. Then, as you can see, if I take out this little m1, so I can write this Fg as the G, and let's say I could be maybe having a Ernie on top of the Earth, like that. Then mass of a Ernie and the mass of a Earth. And the distance between them is going to be the gravitational force between Ernie and the Earth, both of them, towards each other. So I can put this mass of the earth outside, just organize this equation, right? By putting it like this. I just organize it like this. Then we have mass of the earth, and then the mass of the earth times the constant divided by the distance between of them together. On the surface of earth, this distance is equals to just the radius of the, oh, I hope you don't hear my child crying. Anyway, that's going to be the distance between the two objects. It's going to be just the radius of the earth if you're standing on top of the ground, right? So then we can just say this gravitational force, we always just write it like this: mass times G, ME, mass of the earth, divided by the radius of the earth square. And this part is equals to little g, right? And in the last lecture, I calculated this to be 9.8 meter per second squared, right? So it's nothing surprising that we get mg, mass times g. How about when I go up on the mountain? So let's say if I'm climbing on a mountain. So this is going to be the height of the mountain, and then the radius of the earth. So then now the r, or the distance, becomes re plus h. This is going to be just the altitude, or the height from the sea level, ground. So let's see. I'll show you. You can see that so you can see that G is equals to gravitational acceleration constant times the mass of Earth, and then this r squared. That's the acceleration. I hope you see that, mg. See this part. So g is this. And of course, as r increases, g decreases. By how much? So let's see. On the ground, we said on the ground, h, which is the height from the ground, and then a little g, which is meter per second squared. And let's say if you are 70 kilogram, your mass is 70 kilogram. So that's about 154 pounds on the ground. Okay. How much is your gravitational force? So on the ground, you have a zero. Height is zero because you're just on the ground. So we say it's 9.83 meter per second squared, right? And then if you are 70 kilograms, that time 9.83 is 688 Newton. That's how much of the gravitational force is applied. So mass times little g, 9.83. But let's say if you go up higher onto a Mount Whitney, which is the tallest mountain in California, and uh, in the United States if you don't include Alaska. So the Mount Whitney, the height of a Mount Whitney from the ground is 4,500 meters. So it's 4.5 kilometers. Then let's see if I want to find that. That's going to be ME, right? That's going to be RE, the radius of the Earth, times the height square. So you put ME is equals to 5.972 times 10 to the 24 kilogram. Radius of the Earth is 6.365 times 10 to the 6, I believe, meter. So adding the 4,500 compared to the 10 to the 6, you can see it's not too much, right? R becomes 6 point, what is it? 6 point maybe 4. 6.365 10 to the 6 plus 4.5 10 to the 1, 2, 3. 3. See, it's not too much. Look at this order. Yeah, so it's not so much. Anyway, because of that, the gravitational acceleration when you're on the Mount Whitney, it's only 9.82 meter per second square. Yeah, it decreased a little, but not significantly. For example, when you had a 688 Newton, when you're on Mount Whitney, how much did you decrease? It's only 787 Newton. Okay, why don't we fly up all the way up? So jet airplane, they typically fly at 10,000 meter. 10,000 meter. But look, it's still 10 to the 4. Compared to the radius of the Earth, it's 10 to the 6. So it's nothing compared to the Earth's radius. You're just like flying right here, right? Almost touching it. It's not that high. Then the distance between, as if like maybe you're a little bit farther away from the center of the Earth, but not too much farther away. Therefore, the gravitational acceleration is still 9.80 meter per second square. And how much do you weigh now when you're 70 kilograms? You weigh a little bit less, 686 newtons. So do you think it's better to go all the way buy $1,000 airplane ticket to go to do the physical exam? So you're gonna get have without going through a real diet? No. Well, first of all, you're not changing your weight really. But anyhow, you don't really lose much force. You're still going to weigh 686 Newton. I'm saying weight here, but it's not a weight. It could be a weight, but gravitational force is 686. All right. So, International Space Station. How about if you fly all the way to the International Space Station? Where is that? ISIS. How high up is that? That's actually 400 kilometers up high. So 400,000 meter. So now 4.0 times 10 to the 5 meter, right? It's getting up high. However, still compared to the 10 to the 6, on Earth, you're still like only here, not too much. This is where the astronauts are. And that's, the little g is 9.53 meter per second square. And how much of the gravitational force? 667 Newton. You still have a gravitational force, 667 Newton in a space station. But you see this Ernie, if this Ernie is in a space station right now, you're not that, why he's not like this? Why he's not like that? Why he could be floating? When you see all those video of the astronauts in the space station, they send us the video and then they're all floating, weightless. But I calculated, and you can calculate, that it's 667 Newton if you are mass of 70 kilograms. Does this make sense? What's going on? So how do we measure weight? We say, what's the measure? I go to the doctor's office or at home, I step on a scale, right? And inside the scale, there's springs inside, and then I step on it, and the scale reads and gives the force back at me. So this is what the scale reads. The value here. It's the N, the normal force. It's the normal force is what the scale reads. So this represents the weight, how much you weigh. It's not necessarily the gravitational force. Gravitational force is just purely put it into this universal law of gravity, and you can find a gravitational force on you. But what scale read as your weight is the weight. Normal force. Imagine that when you're in an elevator, you're in an elevator. Okay, let's say this elevator just about to start going up. So starting to go up from rest. So initially the velocity is 0, and then you got on the elevator and it starts going up. Which direction is its acceleration? Up, down, right, left? No. Which direction is acceleration? Acceleration of this elevator that just starts going up is this, upward, right? Upward. That means if you have an acceleration, you must have net force, non-zero net force. That's in the same direction as acceleration by following the Newton's second law, right? What are the forces exerted on you? You always have a gravitational force, vertically downward, Ft, and you have normal force. Okay. Normal force. And this normal force, when you are not moving, when you're, or you're in a constant motion, when the net force is 0, then you always have a normal force that's equals to the gravitational force, and they cancel out each other. But when you're in the elevator that you are accelerating upward, this normal force has to be bigger than the gravitational force, so that the net force has to be upward because of this. So normal force now is bigger than gravitational force. So when the normal force is bigger than gravitational force, then you feel heavier because normal force is bigger than gravitational force. So you actually weigh more. And you've done when you might still do when you're going to the elevator and then the elevator is just starting to accelerate, just about to go up. Then you feel heavy. And actually your weight does go bigger because the elevator floor is going to push you to go up. So your weight actually increases. Your gravitational force doesn't increase. Your mass doesn't increase. It's your weight that increases. Okay. How about this elevator now? So now it start going up, right? And then on you, I could be having a scale, I guess. Now it's reached a high floor. So it's reaching a higher floor. That means it's about to stop. But your motion is moving upward and then you want to stop. So acceleration has to decelerate. That means you need to have acceleration that's downward, right? So now the direction of acceleration changes into downward to stop. When you're moving upward, you got to slow down. So it's now downward. The direction of a net force is also has to be downward by following the Newton's second law. What are the forces exerted on you? You always have a gravitational force, and this does not change. But now you say that net force has to be downward. So normal force has to be less than a gravitational force. So now the normal force has to be less than a gravitational force to have the net force downward. So it's less. So how do you feel? You feel lighter. Normal, so again, the gravitational force doesn't change, but because the normal force has decreased so that you can slow down and stop, you feel lighter. Imagine that you could also think about the acceleration downward in a different case. You're stuck at the high floor, right? And then you are at rest and you're getting to the elevator and you're coming down. When you're coming down, when you're just coming down, acceleration is downward. And then again, you feel lighter. So it's not the motion, up or down motion. It's about the direction of acceleration that matters. All right? Let's see in that case. So you're coming down, moving down from rest. Then you're going to have, again, acceleration. That's downward. What if this elevator cable breaks? What happens if the elevator cable breaks? What happens to this forces on you? When there's no more cable, what are the forces exerted on you? It's the motion of free fall, right? Only the gravitational force. So that means and the cable breaks. So that means normal force is 0. And acceleration A becomes just a G because there's no other force. And the normal force equals 0. What does the scale read? What does the scale read when the normal force is 0? You're weightless. Scale reads 0 because you're no longer in contact with the scale. You don't weigh anything. Again, you have a gravitational force. Your gravitational force hasn't changed, but your weight changes throughout, depends on the direction of acceleration. And whenever you're in free fall, so free fall, by definition, is only gravitational force. That means normal force is 0. Therefore, you're always weightless. So you see that by having an acceleration downward, your weight becomes less. And then when you become the maximum, if you're falling with a gravitational acceleration only, then your weight is 0. Lighter and lighter and lighter as you go down. And if there's no more upward force, then your weight is 0. So it's not that your mass has to be 0 or gravitational force has to be 0 to be weightless. It's not the gravitational force. It is the normal force that's 0 that makes you weightless. Okay. When I so the gravity free fall, that's the condition of a free fall, right? So let's say I throw a ball. Ball is thrown this way, and then if that's how it's thrown, this ball eventually is gonna go down, and then it will hit the ground, right? Because all this time, the only force exerted is the gravitational force. You ignore the air resistance. Then the only force that's applied on the ball is going to be the gravitational force. That's the only force applied. And then that's pulling this ball down. So even though it's moving in a horizontal direction, it's going to come down. That's why whenever you throw, it always hits the ground, right? Let's see. Now I'm going to increase this initial speed. So if I increase this initial speed even more, then this ball is going to come down, but it's going to travel longer distance because it takes a while to hit the ground. What if I'm going to increase the initial speed even more? Then it's going to travel longer distance, but eventually it's going to hit the ground. It makes sense, right? So farther you throw, it takes longer. It goes farther and farther away. But you still need the same constant acceleration is there, so it's going to hit the ground. And what kind of a motion these? If you ignore air resistance, all this, it doesn't matter what initial speed you have. The only force you have is gravitational force only. If you ignore air resistance, even though you have an initial speed in a horizontal direction, the only force you have is vertically downward, and then that's why the ball hits the ground. And that's gravitational force. So it's called free fall. It's called free fall for all these cases. So what does that mean? Free fall means, what's the normal force? Free fall means normal force is zero. Of course, you're not in contact. You're not going to have any normal force. Imagine you increase this initial speed, bigger and bigger and bigger, right? So I made it bigger and bigger and bigger. Eventually, Earth has some curvature. For example, it's not completely flat forever. We know that Earth is round, right? So, for example, if you move 8,000 meters far, you will be going down about 5 meters. That's the curvature of the Earth. So I throw, and it's going to hit the ground, it's going to hit the ground, it's going to hit the ground. But if I throw faster and faster and faster, eventually, if I'm throwing the ball, go farther and farther. But if I throw maybe fast enough, this ball will go around and around and around, and it's never going to fall. Never hits the ground. What's that? That's a satellite in orbit, right? Closed orbit or space ISIS. ISIS is going around the Earth. So what's that mean? These satellite and ISIS, they are constantly in free fall. They keep falling around the Earth. But because their initial speed was fast enough that they just keep falling. They don't hit the ground because you had enough horizontal velocity that it just keeps falling forever. So satellite and ISIS, they keep falling and they're in free fall. So what's that? If you're in free fall, that means only force that you have on inside the ISIS or satellite, you're still going to have gravitational force. You need a gravitational force so that it can fall. It can keep falling. Without the gravitational force, you can't keep falling. So you're bounded around the Earth using the gravitational force. But the key thing is it's only so that normal force is constantly zero. When the normal force is zero, you are weightless, right? When the normal force equals zero, that means you're weightless. You're floating. So that's what's happening with the satellite or the ISIS. So we say the gravitational acceleration and we have a gravitational force. You see it here, right? International Space Station do have quite a bit of a gravitational force. It's less compared to when you're on Earth, but this 667 compared to 688 Newton is significant. You haven't lost too much of a gravitational force by being high up there, right? Because the Earth radius is so large that it takes so much effort to go above the distance of Earth radius. And even though you're one distance of Earth radius, you still have a quarter of a gravitational force. You still have a gravitational force. In fact, the gravitational force never becomes zero. It can be tiny, 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 tiny by 1 over r squared, right? But then it's never going to be there, zero. So, but anyhow, you have a significant gravitational force in the International Space Station. But the reason why all the astronauts, they're floating is because they're in free fall. They're orbiting around the Earth using the gravitational force that constantly they're in free fall. And when they're in free fall, normal force is zero, not the gravitational force, and that's why you feel weightless. I have another one to show you. Let's see. Google Chrome. Okay, let's do this. Okay, so here. I hope you can see it. So this is the simulation. I wish I wrote this simulation, but I haven't. So there are two rockets. This rocket, either way, I can set the initial velocity, and then the rocket on the Earth, the top one goes the initial velocity to be only in the vertical direction, and the rocket at the bottom of the Earth has the initial velocity only in the horizontal direction. Either way, the initial velocity is going to be the same. So let's send this rocket with initial velocity of, how about this? 2 kilometers per second. That's fast. In 1 second, it moves 2 kilometers. So that's quite fast, right? And let's fire it and see what kind of a motion will this rocket will do. All right, so fire. Okay, that's so much initial velocity, but it's not enough. It's still it doesn't meet the curvature of the Earth. It still hits the ground. Reset. Let's do 3. I doubt that it's going to make it though. It went a little bit farther, but of course it hit the ground. Reset. Let's do 5. 5 kilometers per second. So each second it's going to move 5 kilometers. All right, fire. Remember I said 8,000 meters for 5 meters down. So 6.5. Oh, you went farther, but still hit the ground. 7. Almost right. 7.5 kilometers per second. Still hit the ground. I am going to do 8. See, once if he has the initial speed that's large enough, then this rocket keep falling, but it doesn't hit the Earth because it has enough initial speed that it can just keep falling, and then it's never going to hit the ground. But you're in free fall, so normal force is 0 throughout this motion. So the astronauts in this space shuttle constantly floating, but you have a gravitational force. And let's see, how much do you need to actually get up? But you can see that it's in orbit, right? So it's in orbit, and then the gravitational force, you have a gravitational force, and that kinetic energy is not quite enough that it's bringing this vertically upward rocket coming back down. All right, so this is going to be a fight between a kinetic energy and a gravitational potential energy. And as you can see, when I increase the speed of the space shuttle, this orange one is making a closed orbit, right? Around the Earth, keeps falling, but it's never hitting Earth. But you see the shape changed. It became elliptical, right? Typically, when the things is in orbit, you're in an elliptical shape. It's in an elliptical orbit. Only at particular velocity, you have a perfect circular orbit. Otherwise, it's usually having some kind of a elliptical orbit. Okay. Anyhow, that's a side note. I'm going to shoot it. This is not something to do with the weightlessness, but let's see if this is enough velocity to see that the rocket is going to be coming back down, or maybe, yep, this is enough initial speed, enough kinetic energy, maybe that rocket won't come back. Looks like it. Okay, I could do 11.5. There's one that almost go and then still come back. This one is also escape velocity. Let's see. 11 is maybe too much. Let's see, sorry. 10.8. Yeah, so if you have enough kinetic energy, then you can get out this orbit, actually. Okay, this one is still your bounded. Come back down. If you're interested, I can give you the website with this rocket simulation. Okay, so you see it. Okay, so this is one thing, and another one. So I mentioned that if you're in this rocket, you're floating, right? Because you have a gravitational force and you're in free fall, so you're constantly free falling, just like the elevator that cable broke, right? So you do have a significant gravitational force that's making you float, because the normal force is zero. In the movie, I think that the last one, the Gravity, the movie that's Gravity, that one they used the cable, but the movie that called Apollo 13, Tom Hanks in it. I don't know if you watched that movie, but Tom Hanks, that's in the movie, they went to the moon. They got in an accident. So there are many scenes, not many, but there are scenes that Tom Hanks actually is floating. And then at that time, they didn't use a cable. And they didn't have that much of a great special effects at that time. But you see in the movie that Tom Hanks is floating. They didn't actually send him to the moon. They didn't actually send him to the space to shoot the movie. So then, how can he be floating? How can he be floating? Okay. Um, when you throw a ball, I'm holding the ball, and then you throw it, this ball gets detached. The whole motion is FG only. ignore the resistance, then you only have a gravitational force. So this is free fall. You could be in an airplane. And then you're moving, you have an engine on, engine on, engine on. But you go up and up and up and up and up, right? You go up and up and up and up and up. But then at the one point, let's say you turn off the engine, cut the engine. If you don't have any thrust, the only force you have is gravitational force only. That means normal force equals 0. So about certain point, and then you still have inertia that's taking you upward. And then this gravitational force, right? Gravitational force is pulling this down, and it's going to come back down. You don't want to hit the ground with free fall, so you turn back the engine on. Engine on, and then you come back up again. So about period from here to here is this airplane is in free fall. That means you in an airplane also in free fall. So therefore you're floating. So the Tom Hanks, you put the camera in and then you make the set like you're in rocket, and then you just go the airplane, and then in the mid-air, you turn off the airplane's engine. Then you're in free fall, go up and come back down. During this motion, you're floating. No special effect. It's a real thing. I have another video that I can show you. It's by OK Go. They always make fun music video. Here. Again. So here it says what you're about to see is real. We shot this in zero gravity. Do you think this is a right comment? Zero gravity? Is there no gravitational force? Wrong. Wrong. It's not zero gravity. It's that zero normal force. You have gravitational force. Gravitational force is the reason why you are floating. Okay? So this is wrong to say in physics. But anyhow, then I'll just show you. In an actual airplane, in the sky, there are no wires or green screen. Enjoy.
Upside down and inside out, and you can feel it. Upside down and inside out, and you can feel it. Don't know where your eyes are, but they're not doing what you said. Don't know where your mind is, baby, but you're better off without it. Inside down and upside out, and you can feel it. Don't stop, can't stop until you feel it going down. I wish I had said the things you thought that I had said. Gravity's just a habit that you're pretty sure you can't break. So when you met the new you, were you scared? Were you cold? Were you kind? Yeah, when you met the new you, did someone die inside? Don't stop, can't stop, it's like a freight train. it's time to decide. Are you here? Are you now? Is this it? All of those selves that you tried, wasn't one of them good enough? 'Cause you're upside down and inside out, and you can feel it. Inside down and upside out, and you can feel it, feel it. Don't stop, can't stop, it's like a freight train. Don't stop, can't stop, till you feel it going down. I wish I had said the things you thought that I had said. Gravity's just a habit that you're pretty sure you can't break. Upside down, inside out, and you can feel it. Don't stop, can't stop until you feel it going down. Upside down, inside out, and you can feel it. Don't stop, can't stop until you feel it going down.
Yeah, so it's a fun video. Some people, oh, sorry. What's going on? I'm sorry. Okay. Some people, they even use in an airplane, you get wet, have a wedding inside this, they call it zero gravity, but it's definitely not zero gravity. It's zero normal force, okay? But you have a gravitational force and you are floating. So this video, it's called NASA's Vomit Airplane, of course, that they use it for training astronauts. And if you pay, I think you can pay like a few $1,000s if you want to be in an airplane to feel the weightlessness. If you're interested, go to Silicon Valley. I think they have that. So you get about 27 seconds of weightlessness. They wanted to video this music video uninterrupted, so they only shot the parts that they wanted, and then when they become a regular gravitational force, they make sure that everybody sat down, and then you even stop the camera, stop the music, right? You didn't stop the camera, you just stop the music, and then when he's starting to have the weightlessness, you turn on the music, and then you did those choreography and stuff. So they did about 8 consecutive, eight course, and that's total 45 minutes of the shooting that they did. So it sounds like it's a pretty hard one. Those 2 females that were in the airplane, they're the trained acrobats. So they seem to be fine and enjoying the ride, being a free fall, the weightlessness. Okay, so this is the end of the chapter 9, and I hope you enjoyed. And yeah, if you have any questions, ask me questions in discussion time. So I'll see you at the discussion.